So in this video, I am going to explain how Laplace transform is used to analyze periodic signals in network systems and understand their behavior in the frequency domain. Let's start with the first scenario, which is a periodic network traffic signal modeled as a ramp function. Here the signal increases linearly within one time period and then repeats continuously. To analyze this, we use SymPy for symbolic computation. First, we define the signal and multiply it by an exponential term. Then we integrate it over one full period. After that, we apply the standard formula for periodic Laplace transform, which allows us to extend the result for the entire repeating signal. The final expression shows how the system behaves in the frequency domain. The important takeaway here is that periodic signals introduce repeating patterns in frequency, which can lead to multiple spikes and affect system stability. So, in this second scenario, which represents a square wave type traffic pattern, this models on and off bursts in a traffic. Like when a firewall detects sudden traffic spikes, even though the code structure is similar, the concept here is different because square waves have transitions. These sudden changes introduce higher frequency components in the system. When we compute the Laplace transform, we again integrate over one period and apply the periodic formula. The result shows that such signals can create strong harmonic components, which may lead to congestion or instability in network devices. Finally, in the third scenario, we analyze a periodic exponentially decaying workload. This is common in distributed systems where task gradually reduces over time but repeat periodically. Here the signal decreases smoothly within each cycle after performing the same steps, defining the signal, integrating and applying the periodic formula. We get the Laplace transform. The key observation is that the exponential decay reduces the higher frequency compound, meaning the system is more stable and dominated by lower frequencies. So overall, this practicum shows how different types of periodic signals behave in the frequency domain. Ramp signals create repeated patterns and square waves introduces high frequency spikes, and exponential decay leads to smoother and more stable behavior. Using symbolic computation makes it easier to derive and analyze these models efficiently.